This video will focus on how water self-ionizes and start to relate it to the concept of pH. So when we talk about ionization, remember what we're talking about is some kind of compound dissociating into the ions. And what's crazy weird about water is that while water is H2O, water actually can self-ionize. Most things, when you put them in water, that's when we talk about them being able to fall apart into their ions because water is so polar and it shields the charge. But water actually can ionize itself. As it moves around and collides with itself, it does what we call auto-ionization. So two water molecules hit together and they make H3O plus and OH minus. In terms of language, this is really important. H3O plus is called the hydronium ion, and OH minus is called the hydroxide ion. So you know that OH minus is hydroxide, so hydronium is the only one that's new. And the reason that's important is because OH minus has to do with the base, H plus has to do with the acid, and the H plus, when it's around water, actually makes the hydronium ion. So when acid increases H plus in solution, it's actually increasing the hydronium ion. Now, if you look at this chemical equation, you can see the mole ratio. Two water molecules, so it's a ratio of 1 to 1, make one hydronium and one hydroxide. So in pure water, as you dissociate, you make equal number of acid, the H plus, as you do the base, the OH minus. Now, it's funny to think about water self-ionizing and acids and bases in water. But I want you guys to be aware that this is a really small amount of ions that do this in water. Okay, so if you have 1 liter of water, like a 1 liter water bottle, which is equivalent to 55 moles of water, only 1.0 times 10 to the negative 7 moles are actually ionizing. So 10 to the negative 7 of the 55. So it's a very, very small fraction that do this. Now, because of this number, that 1.0 times 10 to the negative 7, that means in pure water, we've got 1 times 10 to the negative 7 of the H plus and 1 times 10 to the negative 7 of the OH minus. The concentrations are equal. So in a neutral solution, if you know something about the H plus, you know something about the OH minus. Now, some of you may look at these numbers and might start to bring pH actually to mind, because pH of neutral water is 7. And that 7 actually comes from these concentrations of H plus and OH minus. Okay? So if you're in neutral, neutral means you have equal numbers of acids and bases, and that equal number is always 10 to the negative 7. If you have more acid, the H plus gets bigger. If you have more base, the OH minus gets bigger. So that concept can actually be represented mathematically. Okay? In neutral water, H plus and OH minus have the exact same concentration. They have a 10 to the negative 7 big M, molarity in solution. Now, this is equilibrium, which means if you increase concentration of one of them, the other one has to go down in order to keep your constant the same. The constant, if you remember, your K is always equal to the concentrations of product divided by reactant, but you don't include liquid or solid in your equilibrium expression. So for water, the equilibrium expression for water, which is hysterical, is the concentration of that H plus times the concentration of OH minus. There's no powers to raise them to because there's no coefficients. You don't divide by the reactant because the reactant is a liquid. This is called Kw, the constant for water. And the constant for water will always equal the concentration of H plus times concentration of OH minus. Now, if you look at this numerically, you'll see that the concentration of H plus times concentration of OH minus will always be 1.0 times 10 to the negative 14. And that's a constant, which means that's an always number. That is the product constant for water. In terms of sig figs, you can assume Kw is known infinitely well, so don't ever round your final answer by Kw. So how do we affect our equilibrium? Well, let's talk about an acid shift. If you put acid into solution, what you're putting in there as it dissociates is more H plus. So the stress then is you increase concentration of H+. Remember that the equilibrium always shifts to try to undo what you did. So by you manually increasing that concentration of H+, the system will actually try to decrease concentration of OH- in order to keep the Kw 1.0 times 10 to the negative 14. So now you have a concentration of H+ that's greater than 10 to the negative 7, a concentration of OH- that's less than 10 to the negative 7, and in an acidic solution, H+ is greater than OH-. Now, one teeny tiny math thing to keep an eye on, when I talk about greater than, since we're dealing with a negative exponent, a greater than would be greater than 10 to the negative 7, so like negative 6, negative 5, negative 4, right? Greater than 10 to the negative 7. If we want to talk about a base shift equilibrium, what you're doing is you're putting something in that either increases the concentration of OH- by dissociating, or based on our Bronsted-Lowry definition, it's taking away the H+. Okay? And if you're going to manually take away the H+, the OH- must go up in order to undo what you did, right? So in either case, you're going to be increasing the concentration of OH-, whether it is by removing H+ or physically adding OH- to solution. Now, if this happens, if you increase the concentration of OH-, you're going to have to decrease concentration of H+ in order to keep your equilibrium at 1 times 10 to the negative 14. So in that case, your H+ concentration is less than 10 to the negative 7, your OH is more than 10 to the negative 7, and in bases, your OH concentration is always greater. If you look at this, the maximum concentration based on Kw is 1 times 10 to the negative 14. Okay? So you're always going to be in a range of like 10 to the negative 1 all the way up to 10 to the negative 14. If we put acid or base into solution that exceeds this number, that exceeds your Kw, what that means is we've now gone beyond an equilibrium situation, and we'll have no more of one or the other present. So for example, if you put more acid in so that you exceed the Kw, you will have all acid in your solution. You will have no more base. You are outside of the equilibrium. Now, it's still a reversible reaction. You just literally have driven it all in one direction. Now, you have no more of the other. Now, if you added more, it would reverse because it's a reversible reaction, but that can happen. So if we're dealing with really concentrated solutions of acids and bases, we are outside of the range of what we're talking about. But the reason why this is important is even a small amount of acid or base is very reactive, and we know it's corrosive to humans, it can be bad for the environment, so even a very small amount should be measured. And we're talking, this is so small, but it's a measurable amount and it has an actual consequence. So let's do some math. We've been talking about theoretically how one affects the other, but we can actually use the Kw expression to calculate concentrations of acid or base in solution given information about the other component. So for water, we have an equilibrium expression where the constant for water is concentration of acid times concentration of base. The one thing you need to remember is this Kw is always 1 times 10 to the negative 14. So all I'm going to be giving you is a concentration of one of the two ions. You'll divide it down, and there you'll get the concentration of the other. So the first problem asks, what's the concentration of OH- if you're dealing with this type of solution, 3.0 times 10 to the negative 5 molar solution of HCl. HCl is your acid, so you'll plug in that number for your H+. In order to solve for OH-, then you divide this down. The only thing to be careful of is if you don't know how to use your E key to do this exponent, then you have to make sure to put this entire thing in a parenthesis when you type it in. Otherwise, you'll end up dividing 1.0 by 3 and then timesing your whole thing by 10 to the negative 5, and you'll get a larger exponent. Remember, your exponents have to be between negative 1 and negative 14 to be within this equilibrium expression. So when I solve this, I get the concentration of OH- is 3.23 times 10 to the negative 10, and that's a concentration. Now the second question, is this solution acidic or basic? You can look at your numbers now. So I have 10 to the negative 5 acid, and I have 10 to the negative 10 base. Whatever number is bigger tells you what the solution is. So since 10 to the negative 5 is a bigger concentration, I have more acid in solution than I have base. So the solution is acidic. So second problem, same situation, Kw equals concentration of acid times concentration of base. In this case, I asked for H+, if I give you the concentration of NaOH in solution. So that NaOH is what you put in for OH minus, because that's your base. And then you divide it down, same as we did above, 1.0 times 10 to the negative 14 divided by 6.90 times 10 to the negative 4. Again, make sure that you use the E key or you put this in parentheses. And if you do that, your final answer should be 1.45 times 10 to the negative 11 molar concentration. Same question, is it acidic or basic? This is your acid, this is your base. Since you have more base at 10 to the negative 4 than acid, which is 10 to the negative 11, this solution currently is basic. One more problem to try with you guys. If you look at this, if I mix 10 mils of 0.1 molar HCl to end with a final volume of 500, what will be the concentration of hydroxide? If you look at this, there's more than just one number. So you can't just stick any number in for HCl. And if I look at it, okay, I mix 10 mils and I end with a final volume of 50 mils. Okay, that's a dilution. I'm taking a concentrated solution and I'm diluting it up to 500 mils. So in order to get my concentration of H+ that would allow me to calculate my concentration of hydroxide, I need to carry out a dilution first. Dilution's M1V1 equals M2V2. If I have a 0.1 molar solution and I have 10 mils of that, the question is, what's my new concentration if I dilute that up to 500? And if you solve for that new concentration, you'll get a concentration of 0.0020 molar. So that's your new concentration of HCl, and that is what you will plug in to your Kw expression for the concentration of H+. Okay, so that is my concentration of H+. From that, I can get the concentration of OH minus because these are in equilibrium. If this goes up, this goes down. So this number is eventually going to come down here and divide. And if I do that, I get a concentration of base to be 5.0 times 10 to the negative 12. Is the solution acidic or is it basic? I have 10 to the negative 12 base, 0.002 acid. I have way more acid in solution than base, so the solution is acidic. In the end, the goal of this is just to help you see how H+ and OH are in a relationship with one another and show you that if you have H+, you have OH minus. It's just a question of being able to do the Kw calculation. Okay, go ahead and do some practice and then the form, and have a nice night.